Hello, so here we will discuss the amplitude modulation, which is also called double sideband suppressed carrier modulation. Now, basically what is modulation? So it's a process that causes a shift in the range of frequencies in a signal. So we have let's say a signal that is at a lower frequency range. So we want to shift the frequency range to higher frequencies or any frequencies of our choice. We can do that through modulation. There are two communication types basically. One is the baseband communication, which does not use any modulation, and then the other one is carrier modulation, which uses modulation. And so baseband is generally the range of baseband signals is let's say in the 4 kilohertz for audio. For video it's around 4.3 megahertz. So generally it's in the low frequency region and cannot be transmitted directly through the antenna. So that's why we require modulation to do that, to transmit the signals through antennas. And also the another benefit is we are able to transmit multiple signals through a channel. So in analog modulation, as amplitude modulation is an analog modulation, a basic parameter such as amplitude, frequency or phase of the carrier is varied in proportion to the baseband signal MT. So accordingly, if we are varying the amplitude of the carrier signal, it's called amplitude modulation. If it's the frequency or phase we are varying, then it's called FM and PM. So in this case, the baseband signal MT is called the modulating signal, and the carrier is the signal that is being modulated. So why we use modulation, as I mentioned earlier, to use a range of frequencies more suited to the medium. So certain range of frequencies may be less attenuated by the medium, which could be a coaxial cable, it could be fiber or the wireless medium. So we shift our signal to those range of frequencies. Furthermore, it allows us to transmit multiple signals, more than one signal at a time through the channel. This can be done by frequency division multiplexing. So we assign different frequencies to different channels, and that's how we can transmit them all together. And finally, we can have very small size antennas for high frequency signals. If the the size of the antenna and the frequency of the signal, they are reciprocal to each other, inversely proportional. So if the frequency is high, the size of the antenna is quite low, which is quite convenient as we can have some portable devices, for example mobile phones, on which the antennas are of small size. So let's look into some expressions of the amplitude modulation. So this is the carrier that we will be modulating. So it's basically a sinusoidal signal. It has a radian frequency of omega c. It has a phase generally with respect to some reference, so we will consider it as 0 for most of the discussion. The modulating signal is MT. For example, it's represented by this plot. So if we look at the Fourier transform, the frequency domain representation of this modulating signal, so it occupies this this low frequency region. So this is just a representation. These are not actual shapes or signals. So with amplitude spectrum, so generally we represent the amplitude spectrum by capital M omega. The time domain plot is represented by MT. Now after modulation in the time domain, the signals look like this. So this was the modulating signal, and now after modulation the time domain signal will look like this. So you can see the amplitude of the sinusoidal signal is now the envelope of the sinusoidal signal is now adjusted according to the variation of the signal MT. So that's why it's called the amplitude modulation. Generally we forget to plot the negative side of the time domain plot, because So this comes from the multiplication of the negative values, the minus values of the sinusoidal carrier. When we multiply it with this part of the signal, so the overall result is negative, and so the time domain plot has excursions on both the positive and negative side. So the block diagram looks something like this. This is the spectrum of the baseband signal, the modulating signal MT. We multiply these two signals, so this is the product that we get, MT multiplied by the carrier cos omega CT. The output is MT cos omega CT, which in the time domain looks like this, and in the frequency domain it looks like this. So what happens here in the frequency domain is that we have a a low pass signal. The spectrum of a sine wave is composed of two impulses that are located at omega c. So if we have multiplication in the time domain, we will have convolution in the frequency domain, and so after convolution of these two signals, this is what we get. So this spectrum of the modulating signal has it now appears on the both of the sides at omega c and at minus omega c. This is due to the convolution between the two spectrum, and the lower upper sideband and lower sidebands can also be seen in the plot. So the modulated signal is shown here. So before modulation, this is the MT. This is the spectral plot of MT, the baseband signal. After modulation, this is the time domain signal, and this is the frequency domain representation of the modulated signal. As we saw earlier, it was called a DSB-SC, double sideband suppressed carrier signal, because you can see it has it's on both of the sides of the y-axis, and then there is no carrier over here, so that's why the carrier does not exist, so it's called the suppressed carrier signal. So the modulated signal, let's study some more about it. So the omega c, the carrier frequency, should be greater than at least or equal to the bandwidth of the modulating signal. Otherwise, if this is not true, then these two side bands, they will actually overlap over each other, and it would be difficult to retrieve the signal at the receiver. So this is the time domain expression, and taking the Fourier transform of this expression, we get the frequency domain, which we can see is composed of these two terms, and this is, as mentioned earlier, we obtain it through the convolution of the Fourier transforms of MT as well as the carrier signal. So how do we demodulate this? So basically, demodulation is quite simple. One of the techniques is to multiply the incoming modulated signal. We multiply it again with the same carrier, so the carrier should have, the local oscillator should have exactly the same frequency as the frequency of the sinusoidal carrier on which the signal is modulated. So when we multiply them again, we get a signal ET. What is this ET equal to? The expression is shown here, MT cos square omega CT, because there is double multiplication. If we open this through the trigonometric identity, we get this term. So you can see here we have an MT, which is the baseband signal, and we have a product of MT with a high frequency carrier. So if we use a low pass filter, we can easily filter out the baseband signal at the output. So this is the way we can separate or we can extract or demodulate the signal MT from the modulated version. If we look at the spectrum or the Fourier transform of this ET, it is denoted by E omega. It's equal to half m omega, so the Fourier transform of this, and we know the Fourier transform of this, it's multiplication in the time domain, so after convolution we get these two spectral profiles. So if we look at this spectrum E omega in the through the plot, we will see that we have these components at twice omega c. so they can easily be rejected. We can use a low pass filter to extract this part which represents only the modulating signal. So this method of recovering is called synchronous detection. So we use a carrier of exactly the same frequency and phase as the carrier used for modulation. So for demodulation, that means we need to have a local carrier at the receiver in the frequency and phase coherence with the carrier that is used for the at the modulator side. So you can see from here it's a bit complex to get exactly the same carrier at the exactly the same local oscillator at the receiver. It should have the same parameters as the local oscillator at the transmitter, the modulator. So we began our discussion of AM by introducing the double sideband suppressed carrier signal, because it is easy to understand and to analyze in both time and frequency domains, as we saw in the previous slides. So DSB-SC is not simple to implement basically. So the reason is it requires coherent demodulation, as we saw. So getting a local oscillator that is synchronized with the incoming carrier is quite a challenging task. So it requires a big, actually, a significant circuitry to perform this task. So this requirement is not easy to achieve in practice, because the modulated signal may have traveled hundreds of miles and could even suffer from some unknown frequency shift. So when the signal travels over the channel, it gets frequency shifts. So what are the reasons for frequency shift? So basically, one of the main reasons is the Doppler effect. So if you remember, if this is the source of the signal, if it's coming towards us, then the received frequency is slightly higher than the actual frequency. And if it's moving away from us, like in this case, so the received signal frequency is slightly lower than the actual one. So based upon the distance and the movement of the receiver, the frequency will be different. So now you can see it would be very difficult for the receiver to track these changes and have a local oscillator of the same frequency as the modulator. So now let's look at the received signal characteristics. So this is the received signal here. Here we have the carrier, the amplitude. Then you can see there is a delay in the baseband signal. We have a shift in the carrier frequency, and then there is a delay as well. So where are these parameters coming from? So basically this term, when this is multiplied with TD, this term can also be written in this way, where we have actually opened these brackets. So cos of omega c plus delta t, this t is being multiplied with the term in the bracket, and minus theta d. So what is theta d? It's equal to this term, where this t naught is the unknown delay that we can see here. So it depends upon the length of the link. We don't know the length of the link, which means the distance between the transmitter and receiver. So for example, in an AM system, we don't know where is the transmitter. So the delay between the transmitter and receiver would be unknown. So there would be a phase shift of amount of theta d, which is equal to these terms. So to utilize coherent demodulator, the receiver must be sophisticated enough to generate a local oscillator purely from the received signal. Now the receiver needs to use this signal to get the local oscillator, but the problem with this signal is its frequency keeps on changing depending upon the distance of the receiver. So if the receiver is moving, for example, we are in a car, so then this becomes very difficult. Such a receiver would be harder to implement and could be quite costly. Many receivers are used generally in a broadcast system, so we cannot have so many complex and costly receivers. So alternative to coherent demodulation is for the transmitter to send a carrier along the modulated signal. So one solution is to just send a carrier along with the transmitted signal, the modulated signal. So but in that case the transmitter would need a much higher power level, so the transmission power would be quite high. We can afford this in a point-to-point link, but for broadcast systems transmitting such high powers all the time is it's going to be very expensive. That's again another problem. So generally broadcasting systems tend to favor the trade-off by migrating cost from the many receivers to the fewer transmitters, but it's still, this technique of sending the carrier is still better than the coherent demodulation technique, where the local oscillator extracts the frequency from the received signal, because in this case we can have a few expensive transmitters, but the receivers would become generally low cost because they do not need to produce the local oscillator. Now another solution is to transmit the signal by using a full AM signal. So what is a full AM signal? So let's say we have what we have seen until now is that this is a carrier, this is the modulating signal. When we multiply these two, we get an AM with suppressed carrier. Now let's say if we have, so this is the AM signal that we have obtained until now. So let's say if we add this carrier to our AM signal, then in other words it can also be written in this way. So this would be called a full AM signal, because it not only has the sidebands, it has a carrier as well. So the spectrum of this full AM signal would look like this. So as you can see, this part is the spectrum of the AM double sideband suppressed carrier signal, and after adding this term we get these term in the spectrum. So what are they? If you remember, spectrum or the Fourier transform of a sinusoidal signal is composed of two impulses only. So these are the two impulses that we see. They are at the frequency of omega c and minus omega c. So this is the spectrum of the complete full AM signal. Now how do we implement this full AM? So for double sideband we first generate a DSB-SC signal with suppressed carrier. So this is the output. So this is the technique that we studied until now. If you want to make it a full AM, so we have to add some constant to this signal MT. In other words, it's like clamping this signal to a higher value, and then we multiply the carrier with it. So then at the output we will get the full AM signal. Now how much should the value of this A be equal to? So this is discussed in the coming slides. So we have a signal like this. For example, this is the signal, this is the peak value of this signal. So if this A, we add an A to this MT, so you can see that this will go up. It will be clamped to a higher amplitude. So after that, if we perform the modulation, if we multiply this signal with a carrier, this is the output we are getting. So this is the full AM signal. So from here we can see that the complete profile, time domain profile of the signal MT can be seen from here. This is the benefit of the full AM signal, that it becomes easy to extract the variations, the time domain variations of our baseband signal. So now you see, if we want to completely extract the time domain variations, so the amplitude of A should be greater than the maximum peak of the modulating signal. So in this case, for example, if it's not greater than, the amplitude is not high enough, so we will have a signal, AM signal like this. So we will have the negative excursions as well. So it becomes if we look at the positive side only, so we will have a signal like this. So that becomes it becomes difficult to extract a signal which has this kind of an envelope, right? So in summary, the amplitude A plus mt must be greater than or equal to 0. So in that case, all the excursions of the positive amplitude can be easily separated from at the demodulator. So let's say MP is the peak of MT. So then, and we have A greater than or equal to MP. So in that case, we can use an envelope detector. So we will be discussing envelope detector in another video. From these two parameters, we get the modulation index, which is the ratio of MP by A. This modulation index is always between 0 and 1, right? So if this is between 0 and 1, so then we can perform envelope detection. So we don't need to perform the coherent or synchronous detection as we discussed previously. So what is envelope detection? We'll quickly look at it. So we have a signal MT. This is the modulating signal. Modulating signal amplitude in this case is B. So the modulation index is this B divided by A, the amplitude that we add to the signal. And so modulating and modulated signals are shown here. So this is MT, which is B cos omega mt. So remember this is omega m, so this is the frequency of the message signal, not the carrier signal. So after AM has been implemented, so this is the time domain representation of a full AM signal. We can substitute the value of MT here. So we have considered the message signal as a sinusoidal signal having a low frequency. So this is called tone modulation, right? So then if we look at the AM signal in detail, we have two parts. One is the carrier A cos omega CT, and the other one is the sideband. So this was the double sideband suppressed carrier, and this is the carrier part. So the power of the carrier, now we'll see how efficient is the full AM technique. So the power of the carrier A cos omega CT is A square by 2. The power of the sidebands is M square T by 2. So this is the average value of MT, so the RMS value in fact. So now the power would be, the efficiency would be equal to the useful power divided by total power. The useful power in this case is the power in the sidebands. The total power is power in the sidebands plus the power in the carrier. So and when we multiply it with 100, it gives us the efficiency as a percentage. So this is how we calculate the efficiency of a full AM signal. Now let's substitute some parameters. When we have MT is equal to mu A cos of omega MT. So this is, let's say, a tone modulation. Our baseband signal is a sinusoidal signal. Signal power is equal to this. In that case, let's say, because the modulation index can be between 0 and 1, let's say we have a modulation index of 1 unity, so that will give us the maximum efficiency as 33%. If we use any other value of modulation index, the efficiency would be reduced. If we use any value less than 1, the efficiency of the system will be reduced. So to summarize the discussion, we first saw the double sideband suppressed carrier modulation in AM. We saw that the only way to detect it is or demodulate it is to use a synchronous detector to have a local oscillator that has the same frequency as the incoming carrier. Then after that, we saw another technique as if we don't want to have if you don't want to generate the local oscillator at the receiver, we can also transmit a full AM signal where the transmitter transmits the carrier along with the double sideband signal. So after that, we saw some characteristics of the full AM signal such as efficiency, etc. So this basically is the complete discussion. If you have any questions, you are feel free to ask in the comment section.